Welcome to the 16th video of this course in quantum processing. Last video we introduced the idea of Bose-Einstein condensation using the very low temperature fashion that we encountered in the video for laser cooling and evaporative cooling merging together and introduced by Eric Cornell, Carl Wyman and Wolfgang Ketteler groups at Boulder and MIT respectively. Feshbach resonance was also realized by the group of Wolfgang Ketteler at MIT in 1998 when they tried to use magnetic field to knob or tune the interactions between atoms, forming molecular pairs, as we will see in a second. So let's consider that you have a Born-Oppenheimer channel that looks like this, the potential looking like this, and for the black curve you see here is the open channel. So let's call it the open channel for two atoms, for example. This open channel has an energy matching here, just energy difference here for the energy of the collision for the two atoms. The red curve you see here is called the closed channel curve. So this is, let me mark it with, label it with red here, the closed channel. You can go from this channel to the other channel of the closed channel by the knob of a magnetic field. So the magnetic field, static magnetic field, you can tune the pairs. They exist actually as pairs of spin configurations, and that with higher energy corresponding to the different spin configuration of, let's say, a singlet state, for example. Here is S0, here is S1 for a triplet state, and you can tune actually the closed channel getting upward and downward by the action of a magnetic field gradient that you can affect the system with, the quantum system with. Actually, this state, closed channel state, has some energy at this range. It's called a bound state. So we can form a bound state for two atoms, and this bound state can coincide with the energy of the collision by also the action of magnetic field. This is what I call Feshbach resonance, that you can actually go from a state closely or very strong state, bound state, to non-bound state, and vice versa by the magnetic field that you can affect the system with. So let's take another look, or two looks actually, at those two curves or those two diagrams you see here. Consider the left one first. So this is the curve for scattering length and magnetic field in axis of y and x respectively. The A, this is the scattering length of atoms. Scattering length is characteristic for the elastic collision. If you have two atoms that looking like this, and the scattering length, you can scatter both of them elastically away or together, inward, outward, or whatever. So if you draw a diagram that is representing the magnetic field, so let's say this is the curve for the this is the axis of the magnetic field of two atoms. So if you apply positive magnetic field, you see here, for scattering length that's larger than 0, here actually you call it repulsive interaction. This is effective repulsive interaction. So this is repulsive interaction, because actually the magnetic field affecting on the scattering length is larger than 0, and on the other side of the field, on the other side of the axis for the scattering length, here is negative. So it means that this is very attractive interaction. So for A, let's label it with, let's label it with black here. So A is less than 0 for very attractive interaction. Okay, so what about this point that the scattering length is 0? Nothing happens actually. This is just a quantum pair for a gas that there's no non-interacting, for the scattering length is equal to 0. So you have complete exquisite control over the interaction or non-interaction of the system by the magnetic field that you see here. Another curve or another diagram for, it's actually not curve, this is a diagram for the magnetic field, looking in terms of energy. So in this region, let's separate it like this. In this region where the scattering length is actually less than 0, so this is for pairs that are actually non-interacting, non-bound state. And by the action of magnetic field sweeping, you can go from an unbound state to bound state here, and this bound state is a molecular pair. So you form a Feshbach molecule. Here just you form a, before forming a Feshbach molecule, just separating two atoms, which are Feshbach atoms, as you see here. So ultra-cold atoms can be manipulated this way, can be tuned this way. You have two ultra-cold atoms, you go into ultra-cold molecule. Those are characteristic. Both regions here and here are characteristic. Here the scattering length is larger than 0. So looking at those special, okay, let me fit it. Looking at those special regions you see here, you can see that this is a long-range interaction. Okay, this is attraction between the two states, two atoms here. This is forming a Cooper pair. This is what I call Cooper pairs. We will see in a second the difference between Cooper pairs and fermion pairs forming Bose-Einstein condensation. But the other molecular pair you see here, this is a tightly bound molecule, the tightly bound fermion pairs that are forming repulsive interaction, but this is a stable molecular pair, as you can see. So you can go from side to the other by the magnetic field gradient that you affect the system with. Actually, the last thing that I would like to mention, the difference between Cooper pairs, we call it BCS pair for Bardeen, Cooper, and Schrieffer. And those guys form important concept in the field of atomic physics, that you can tune the magnetic field to go from this harmonic trap, or it's not harmonic trap, just harmonic shape, into a BCS shape from BEC to BCS. BEC are some bosons that are occupying the ground state of our harmonic system here, and actually if Bose-Einstein condensation is called a superfluid state. So this is a superfluid state, superfluid for bosons. For the other case, for BCS, they just separate, so there are Fermi pairs here, weakly interaction between the Fermi pairs. Those pairs here form very weak interaction, but for Bose-Einstein condensate, they are imprintable fermions that occupy the same state, but the two fermions together form a boson, and two fermions together form a boson, and the other form a boson for this case. You can go from BEC to BCS by the magnetic field and vice versa. Okay, so this was just a quick flavor for Feshbach resonance. It's very unique technique we use in, or they use in everyday experiments for getting from state to the other by this kind of magnetic field affecting the quantum states of the system. Thanks a lot for watching, and see you in the next time.